In the last video, we talked about using the tangent plane and linearization and the differential as a way of approximating a function of two variables or even more variables. However, it's not always the case that it's a very good approximation. Let's take a look at an example. Let's look at the function f of xy, which we want to be equal to xy over x squared plus y squared. Of course, that can't always be true. If x and y are both 0, then that's not going to work. So we'll specify here that xy is not the origin. And instead, at the origin, we're going to assign it a value. We're just going to say it's equal to 0 at the origin. If we look at this function, let's actually go ahead and plot this. We see that we get this kind of pinched plane that we looked at back in 14.2. At the origin, this function doesn't really look like a plane at all. And in fact, it doesn't matter how far we zoom in, we never looks like a plane. In fact, it kind of looks like we have two crossed planes, if we're really being honest about it. We wouldn't really expect there to be a linearization for this particular function at the origin. It just it doesn't look like it should be linear in any sort of way. In fact, the function here isn't even continuous because there's no limit to xy over x squared plus y squared as xy goes to 0, 0. However, we can find partial derivatives at 0, 0. The partial derivative of f with respect to x at 0, 0, well, keep in mind what we're doing there is we're plugging in 0 for our y value and then taking the limit to find the derivative. So if we put 0 in for y, the top of this is 0, the bottom doesn't really matter as long as it wasn't 0 to begin with, but we're not considering at the point 0, 0. We're considering points close to it. So we're looking at the limit of the 0 function. And so the derivative of the 0 function is 0. And so that's what we get. Same thing if we look at the derivative with respect to y. We get 0 there as well. So it does have partial derivatives, but it's not continuous. So what does that mean? Well, if we use those partial derivatives of 0 and 0, and we use our formula for the tangent plane, we would get the plane z equals 0. And it really I shouldn't have to tell you that this does not really approximate the plane around this point. This doesn't have the feel of a tangent plane or a linearization in any way, shape, or form. Things just feel wrong here. Let's modify this example a little bit. So this is the example that they gave in the book. I wasn't quite satisfied with it because they did give us a function that wasn't continuous there. Let's look at one that is continuous at 0, 0. Here, all I'm going to do is I'm going to take the y that they have on top, and I'm going to square it. Everything else is going to stay the same. In fact, we still have to fill in that 0 at the origin. So if we go ahead and plot this one, in fact, I'm just going to go ahead and modify this. We get a function that you can pretty clearly see is really crinkled at the origin, but there's nothing discontinuous about it. In fact, this is a continuous function. And we can also do the same kind of thing for partial derivatives. We can get, well, actually, do I want to actually work out what the partial derivatives are? Maybe we want to do that. We need to differentiate this thing. Actually, wait. Yeah. We can figure out the partial derivatives are pretty easily at the point 0, 0 without having to do the differentiation itself. Because remember, we're just plugging in zeros for x and y. So when we plug in 0 for y, we're looking at the line, you can say z equals 0. We're just looking at a constant 0, so the derivative with respect to x at 0, 0 is still 0. And the derivative with respect to y at 0, 0 is also 0. So we do still have partial derivatives, and this time we do have a continuous function. If we go ahead and plot that plane, that z equals 0, that would be suggested by those partial derivatives, that in some sense is supposed to be our tangent plane. But it still doesn't feel like it's a tangent plane. Things don't feel right here. Even if in some ways it does play the role of tangent plane a lot better, and in fact it would be a better approximation, you might say, than it was in the last example, but things still feel off. So what's really going on here? I guess we can even go a little bit further and ask exactly how far off are we going to be? Well, the point is that we need to insist on a stricter condition than just having the partial derivatives exist, or even having the function continuous along with the partial derivatives existing. So we're going to define, well, okay, so the book defines a function of two variables as being differentiable if this particular condition is satisfied. So here we're saying that z equals f of x is differentiable at a particular point if the delta z being a difference in our z values, we're looking at what is the difference between the z values at 2 points that are close together. And we're saying that as long as we can kind of write down our delta z in this particular form for some kind of unspecified epsilon 1 and epsilon 2 that go to 0 as long as delta x, a difference in x's and a difference in y's, also goes to 0, 0. I'm not too fond of this particular definition, but there's a reason why they're using it. To actually work with this a little bit better, and you might see this if you take a more advanced course in calculus, specifically in multivariable calculus. Usually they'll assume that you have some knowledge of linear algebra, and you'll most likely see something like taking a limit as hk goes to 0, 0 of a fraction where it's taking the difference of f of x plus h and y plus k minus f of xy, but then minus a times h and b times k, where a and b are some constant values, all over, this is actually going to be the norm of hk, the magnitude of that as a vector, you might say. This is a square root of h squared plus k squared. And as long as this goes to 0, then f is differentiable there. That might feel a little bit better, may not. It really depends on you. And there are actually a few issues with this still. For one thing, it doesn't generalize very, very easily. A third way you might see this written, this time using vectors. So here I'm going to use a vector h that's going to 0. You can think of this as hk, but maybe having more than just two variables now. We're going to look at f of x plus h. So here we have vector x plus vector h minus f of x. Then minus, I'm going to write this as a derivative, though I'll have to explain that in a moment. we have to take the magnitude of that, and then we divide by the magnitude of h, and we want that to equal 0. So f prime of x is not a number. So here, this is a function of two variables, or, well, a function of multivariables, you could actually say. The derivative of that, and apply, actually at a point x, which is a vector. It's more than one number here. This thing will actually turn out to be a matrix. And this object is what is sometimes called the total derivative, as opposed to the partial derivatives that we've been working with. So there is a relationship there. We can't really get into it here because we lack the tools in this class to really work with it. I kind of do wish that Calculus 3 in our actually required linear algebra so that we could actually talk about the total derivative here. But the point is that that being differentiable at a point for a function of more than one variable is actually a fairly complicated question. Just like limits at a point for a function of two variables is more complicated than it was for one variable. However, we're going to avoid most of this formality because all of these definitions do lead to a particular useful theorem that we can usually get away with using. So here we have Theorem 8. If the partial derivatives f sub x and f sub y exist near a point and are continuous functions, then f is differentiable. Now, note that this doesn't always have to be true for a function to actually be differentiable. This is actually a little bit beyond what we need. But we did already note that just having the partial derivatives exist was not enough. We do need this continuity condition on those for this theorem to apply. And usually when they exist, they will be continuous. It's not a guarantee. So let's look back at our second example. Remember, our f of xy is equal to xy squared over x squared plus y squared, except at 0, 0, but we're just defining it to be 0 there. If we look at the derivative of this, let's look at the x partial derivative. We have to use the quotient rule here. So we have to take the derivative of the top, with respect to x, by the way, which is y squared, times the bottom, minus the top, times the derivative of the bottom, which is just going to be 2x, over the bottom squared. We go ahead and actually work out what we have on the top there. The bottom is just going to stay what it was, but the top actually can simplify to be y to the fourth minus x squared y squared. And we go ahead and plot that. So we have y to the fourth minus x, oops, I wasn't done with you yet, x squared y squared, and then we're dividing by x squared plus y squared, but that's squared as well. And we get this surface here, which is definitely not continuous at the origin. You can actually see that along the y-axis, we're approaching 1. Along the x-axis, fairly small number, probably like 0.1. I haven't worked out what it is, but you can kind of see what something that's not going to 1 at least. And in fact, GeoGebra kind of has an issue with the function in general and can't really plot it very well around 0, 0. So definitely not a continuous function. I mean, that right there already contradicts our theorem. If we look at the y derivative, we go ahead and do the exact same kind of thing, except now we're differentiating with respect to y instead of x. So we end up with a derivative of the top is a 2xy, still times the bottom, minus the top, times the derivative of the bottom now is 2y. Still have this on the bottom. And if we simplify that, the top is just going to turn into 2x cubed y this time, with the same bottom. And if we plot that one, 2x cubed y divided by x squared plus y squared squared. And let's get that one out of there so we can see it. So again, definitely not continuous at the origin. This time, actually, if you just looked around along the x and y axes, it looks like both of those are staying 0. So those will actually both go to the same value of 0 there. But along this direction, you can tell we're going to a, like 0.6 or something like that. And then down here, instead, we're going to maybe like negative 0.6, something like that. But really, you should be able to look at the graph and tell, yeah, things are not going to be working very nicely at the origin. These are definitely not continuous functions. Now, that doesn't necessarily prove for sure that this function is not differentiable at the origin. It's clear from our surface that we originally had that it is sufficiently weird at the origin that we wouldn't expect it to be differentiable. But proving that something is not differentiable is quite complicated as well. But for the most part, most functions that we're going to be dealing with are going to have their partial derivatives, and their partial derivatives are going to be fairly continuous. So we're going to almost exclusively work with functions at points where they are differentiable. And we'll just go ahead and use this theorem here in order to essentially prove that, even though we normally won't explicitly go out and say, well, I'm going to prove that this is differentiable before I try to work with it. But most of the functions that we expect to be differentiable are going to be differentiable. So like a polynomial, we're not going to have any issues with because it will definitely have partial derivatives, and the partial derivatives will definitely be continuous. So we don't have any issue with those. It's these weird ones where we have discontinuous stuff happening that are the real big issues. But most of the time, we're not going to be really working with these that much. So this is kind of a quicker video than most, but I did want to actually make sure to really get into your heads that all the stuff we were doing in the last video, we have to be a little bit careful with. But for the most part, it won't be that big of an issue for us going forward. So I'll leave it off here. I'll see you guys in the next section.